Hello viewers, so in this video we're going to look at how to calculate change in internal energy, work and heat. From this van der Waals equation of real gases, we can write the P as a subject of the formula as this formula here, the equation here. Okay, we have P, we divide by this one both sides and then we subtract this one. Okay, we take this one to the other side and then it will become minus this side. It will become minus after dividing by this one. Okay, um, let's read here. They say again, accept this identity that they are giving you. They are giving you an identity here. They say the identity is given by du dv at constant temperature is the same as T multiplied by dp dt at constant number of moles and volume. And then we have what? We have here minus P. Calculate delta U work and then as well as the heat, okay? As well as the heat. For an isothermal, constant temperature isothermal, and then for reversible compression, those words are very important. Those are your keywords. At number of moles, one mole and then of carbon dioxide at 300 kelvins, from this volume V1 to V2. Okay, let's answer questions now. If that carbon dioxide that they are compressing here is an ideal gas, okay, now, what will be delta U for an ideal gas? Okay, it's just zero. At constant temperature, delta U for an ideal gas is zero. Moving on to question where we calculate work of this problem. A, we start by, you can always, like your teachers always told you, like you need to calculate number of moles in whatever that you do in case you don't know where to start. This is where you can always start. dw, when you are looking for work, is the same as minus P external dv, and then from here you will figure out what is given and then substitute it into this formula. Okay, but then we are looking for work is the same as the integral of dw, and that is the integral of this minus P external dv. Why do we substitute this into? Because this is our dw. Now I'm substituting dw with minus P external dv there. You see, that's what we are doing. That's basically what we are doing. You're just replacing dw with what is equivalent to, okay, the minus P external dv. But then since we know now, we are going to integrate with respect to volume, because the volume is the one is something that is changing here. Okay, we are going to integrate with respect to it. So you can say from volume 1 to volume 2. That's what we are doing. Okay, and then we look at this, our P external. It was not given. They didn't say it's constant, so we cannot take it out. We cannot take something that is not a constant outside of the integral. We need to integrate over it. So they didn't mention that it's constant, so we don't assume it's constant. By the way, if the volume is changing, it may not be a constant. Let's see what you're going to do. Here they said we have a reversible compression. Okay, that would help us to say our P external is the same as our P internal. Okay, the pressure that is outside is equal to the pressure that is inside, because this thing happens reversibly. These two pressures are at equilibrium, but this one still compresses so that the container becomes small. But as the container becomes small, those two pressures are equivalent to each other, but they are changing as time goes on. The pressure that is outside of the container start off with a smaller magnitude that is equivalent to the pressure of the that is inside of the container, and then they start increasing in magnitude as both of them, they increase in magnitude equivalently so as time goes on until the container becomes 5 liters. Okay, that's what happens. How does that help us? We know now that the pressure here, that is the pressure external, you can replace it with the pressure that is in the inside of the container. But this pressure that is inside of the container is dependent on the number of moles that are inside of that container, and that is just nRT over V. We use this one. We use this fact that for ideal gases, PV is the same as nRT. So we divide by V both sides. It will disappear there and come here. And then the pressure that is inside of the container, the internal pressure, will be given by the number of moles that are in there, multiplied by R, multiplied by T over V. Okay, so we are going to just replace this, our P external, with that. So this is the same as what? the integral of from v1 to v2 of minus p internal dv. Okay, and what does this give us? I'll just continue here on top with everything. This gives us the work now that is equal to the integral from v1 to v2 of what? Of minus nRT over v dv. Okay, and then we have what? We have these constants minus 1 nRT, all of them. We take them outside of this integral. They are innocent. We are looking for volume dv. Integrate with respect to your volume. Then we take minus nRT outside. Here we couldn't take the same applies here. We couldn't take the pressure outside. The P external, we couldn't take it outside. Why? Because it's not a constant. It's dependent on this volume that keeps on changing. Now we wrote it in terms of that volume so that we can take everything that is a constant outside and then remain with 1 over V inside dV. And then we have from V1 to V2. Okay. And then what do we do after this? This is the same as minus of nRT. And then what do we have? We have ln of V. We want to integrate from which limits of integration? From V1 to V2. Okay, from V1 to V2. And this gives us what? This gives us ln of V2 minus ln of V1. That gives us minus nRT ln of V2 over V1. Okay, write like this. And then from here, we can just plug in the numbers. That is, I will open a big bracket and then write the units for work at the end. Okay, I'll do that. But even if you just plug everything in, they will cancel out. Okay, they will have to cancel out and give them the correct math. So we have the bracket here. We'll open a bracket here, and then we will say minus number of moles is 1. R is given by 8.314, if I'm not mistaken, and then multiply by T. Let me just confirm the value of R. Yes, it's 8.314. And then we have T that is given here is 300, the temperature there. Okay, you can see it. We have 300. So we put 300 there. Ln of what? Ln of 5 over 20. Even if we say multiply by 10 to the power of minus here and multiply by 10 to the power of and multiply by the same factor at the bottom to convert them to SI units, they will cancel. Okay, times 10 to the power of minus 3, they will cancel those ones, so we don't care about them. So we can just write this as 5 over 20 here, and then close the bracket, and then save this space for joules. Okay, we'll save this space here for our unit, joules. Okay, and then we put this in your calculator. What do we get? We should get here, we get 458 joules as our final answer. Okay, and then that is for work. How will we then calculate heat? This is how we calculate heat. We say the delta U is the same as change in internal energy is the same as heat plus work, or work plus heat, any way you would like to write it. This guy here, we just calculated him, it's 0. And then we say this one, or we can just write heat as a subjective formula. We say Q is the same as delta U there minus W. And then what is delta U? Delta U is 0 minus W is 3,458 joules. And that is your final answer, minus 3,458 joules. Okay, after writing it like this, we are done. We move on to to part B. We move on to part B, and then we do the same things, the same procedures, but now they are more complicated because we are going to use these ones. Don't be scared by they're going to be more complicated. You will see. We'll go through it together. They also said we must use this identity. This is when you know now you have to use that identity. You see here, it's not an ideal gas. They didn't say anything about ideal gas on the statement. Now we have a real gas, the van der Waals gas. Okay, then we can use that equation. we can use those equations of van der Waals together with this identity to answer the following questions. Let's start with delta U. We are looking for delta U. And this we can get it. It's a state function, yes, but if we can integrate the d of u, okay? If we can integrate the d of u, we will get that delta u. That's what we are looking for. And if you can check this one, is there du. That's where it is. Then that's how we're going to catch it. Okay, let's write that identity down and start answering the question. The identity says du with respect to v. I'm not going to write at constant temperature. That small t here just says at constant temperature. As I'm saying it now, you should put it in your head. We are not going to write that one down. It's going to distract us. We multiply t with what? The partial derivative of p of the pressure with respect to t, differentiate pressure with respect to t, and then multiply the resulting with the temperature that is outside here, and then subtract p from it, and then you will be answering the question. This is we have to simplify the right side here first. After simplifying the right side here first, we can multiply by this guy both sides and then integrate with respect to volume on the other side, on the right side, and then we will get the answer that we are looking for. That's the procedure. Okay. Now let's simplify this guy here first. Okay. We are going to simplify him here. I want to differentiate pressure with respect to T. I didn't write P there with the reason because I want to replace this P with what's P. You see P here for van der Waals P. The van der Waals pressure is given by these guys here. Okay, so I'm going to write them down there. nRT over V minus NB minus N squared A over V squared. We write like that. What is that? This is the same as the guys that are in the bracket there, dp dt. If I solve this successfully, I'm going to replace that with, I'm going to replace this with whatever that is. Okay, let's solve that successfully there and say this is, if I want to differentiate these guys partially with respect to t, only t, the t is my variable and everything else there I see it as a number, as a constant, as some constant. They are all constants. Okay, when I differentiate that, I get what? It's like when you see 2x 2x to the power of 1. It's like this thing to the power of this thing t to the power of 1. Okay, 2x to the power of 1, like that. What do you get when you differentiate 2x? You get 2, right? So this is, there's no need for us to write that. I'm just making it, I just want to make sure that you guys understand what I'm doing. So the answer for this is just n r over v minus nb. That is your constant that is in front of the t. Okay, you put it there, and then t to the power of 1 minus 1, 0, t to the power of 0 is 1, then you put it here. This one doesn't have a t. It's just minus 3, minus 5. Any constant that you'd like to put there goes to 0. That's how you do maths, okay? And then what do we do after here? We can put this guy inside of that bracket here. That's our dp/dt. And then we can say now our du dv is the same as what? Is the same as nr multiplied by t is nrt over v minus nb, right? And then we subtract p. What is p? P is still that one there on top in terms of volume. Okay, we're going to replace it here. So it's going to be minus of the first one, nRT over V minus NB, and then minus, this minus is somewhere here, it's outside there. So it's minus of this, minus and a minus here. They give us what? They give us nothing but a positive sign. So we put positive here, positive of N squared A over V squared. Okay, so I'm going to erase this one here so that we have space, so that we can continue there. So we get that our d du dv at constant temperature is the same as what? Is the same, because these two guys go away, they disappear, they vanished. We have just n squared a over b over, not b, over v squared, like that. Okay, we can multiply by this dv both sides. Okay, and right now our partial derivative of u is the same as the n squared a over v dv multiplying by this guy both sides. That's what we get. Okay, and then after getting this one here, what do we get? We want now to integrate both sides. We integrate both sides, and then we get what here? The answer for that one, we wrote it first here before we wrote this identity. That's what we wrote. The answer for this one is that delta is delta u. And this is equals to, take out n squared a outside. They are constant. They have got nothing to do with this business here of the integral and the dv. Okay, then we take them out. They are innocent. N squared a, the integral of 1 over v. This is supposed to be v squared. I'm sorry. This is supposed to be v squared there. Okay, v squared dv. Okay, and then what do we get? We get the negative of n squared a over v, but I will write it as 1 over v here, and then integrate from the limits of integration. That way, from v1 to v2. Okay, and we should indicate all the way here, from here, v1 to v2. Okay, v1 to v2. But that's small waters. We will be fine. Just remember to put them, please. Immediately when you write something like this, dv, where you're going to integrate with respect to volume, and you know you're going to integrate with respect to, and you know you're going to integrate with respect to volume, that is given, that the volume keeps on changing from 20 to 5. Then that's when you start putting the limits of integration. Okay. Then we have what as the answer? We have minus n is 1, 1 squared is 1, can put there, and then a is 0.3640, and then what do we have here? We have 1 over the v2. Now, because we are going to say 1 over v minus 1, another 1 over v, it's very important for us to now convert them, okay? Because now they are not in front of the line where they were cancelling the units and the conversions. Now we must put them here as 5. The v2 final volume is 5 multiplied by 10 to the power minus 3. You put there 5 multiply 10 to the power minus 3, and then you have 20 there times 10 to the power minus 3. And then what do we get as the answer for this? You put it on your calculator. You should get minus 54.6 joules here. The unit of delta U is joule. We put it there like that. And that is the answer. That's how we get that minus 54. And then moving on to part of the work of part B of work. We calculate work for part B now. We want to start by saying, like I said, you start first by saying we can write it after. That thing that I was about to write, you can write it after this one. After writing, the work is the same as the integral of the work. Okay, and that work, the work, we are going to replace it with what? With minus p external dv from volume 1 to volume 2. We can start here, okay, and then say we're going to replace that p external with what? Remember, they didn't say p external is constant again. So if it's not constant, if they didn't say it's constant, we don't do any. This happens reversibly. That's a hint. Okay, you see just p internal is the same as p external, and p internal is given by these guys here, because now we are dealing with the van der Waals gas. Okay, so just say p internal is the same as p external. We write like that, and then we say this integral is the same as the integral of from v1 to v2 minus of p external. P external, that is the same as p internal, because these things happen reversibly. Okay, we put like that. This p internal is the same as this one. Now it's no longer given by nRT over v, it's given by this one here. That is just the bracket of nRT over v minus nb, and then we subtract what? Okay, we should subtract here before closing the bracket, because this negative is for everything that comes after this bracket. So we have negative of n squared a over v squared, and then we want to integrate this thing with respect to v. All we did on this step is replacing p ext with p internal. P internal, that is this guy here. Maybe I should write it down here so that you don't get lost. This is from v1 to V2 of minus P external is now P internal dV. Why P internal? Because the reversible happens. We explained it earlier on this video. Now, what do we have next? We have the integral of, we can write this as two integrals if that's how you would prefer it, but I prefer to work it out as it is. Okay, so this whole bracket has a negative outside. We are going to take this negative outside of the integral. It's just a constant one, negative one. We put it there. We put negative of 1, integral of what? Integral of from V1 to V2 of nRT over V minus NB, and then subtract N squared A over V squared, and then what do we have? What do we have here? We have dV. We must put them in brackets, okay? Or else we'll have to put multiple integrals here. Here we'll have to put dV and then put the integral here, and then it's going to be a lot of work like that. But it still works out to be the same thing, because the integral of the sum is the sums of the integrals. We can do like that. And here we have what? We have equal sign, or we can continue work. We can continue like this, say work equals to the negative of what? The negative of, now I want to integrate this thing, this first one, with respect to V. Same applies. I see every other guy there as a constant, except for this V, because we are integrating with respect to V. So we've got here a big bracket. Inside of that bracket, we have the nRT. They've got nothing to do with this integral. We take them out, to write them down there, n. Okay, and then we have what? The integral of 1 over V minus NB, my D. We can write D here. We can write like this, from V1 to V2. We can write dV here, separating the integrals now into two integrals. Okay, I'm forced to do this because now we have another constant here that we are going to take out as well. And then we say minus. We don't bother about this negative. It's outside. It's still outside of that bracket there on top. Okay, it's still there. So we don't bother about that one. Just leave it as it is. Excuse it. Focus on the inside. We have dV there, and then what do we have? We have another integral from V1 to V2. Before writing this integral, we should take out the constant, because that's the reason why we are separating the integrals. We have two terms here inside, and then they both have constants on top that we need to take out. Okay, the n squared a, we take it out, and then we integrate over V, 1 over V squared dV. And then we can close this bracket that we opened here. Okay, then what's the next step? The next step is to write now we are close to the final answer. That is just minus nRT. I can write them now. I can multiply this negative inside. That's what I can do. I can just write this as minus of nRT. This integral here with respect to V, I see NB as a constant. Remember, I said everything there is a constant except for the V. Okay, except for the now V. These things like the integral of 1 over x to the power of 1, V to the power of 1, right? And then subtract something, any constant that would like 3 dx. This will lead us to ln of x minus 3 itself. We will have something like this as the answer. That's what we are going to do there. Okay, so we have minus of nRT, we have ln here of what? Of V minus NB, because the derivative of the inside function here, the derivative of this thing with respect to V is just 1. So we divide by 1. There's no need for us to write that one, really. So we just let it be like this. And then we integrate this from the limits of integration that are from V1 to V2. And then we have this negative, multiply with this negative, you get a positive. So we're going to add this. We're going to add here plus n squared a, and then we integrate this guy here. When we integrate that guy, we have a negative of what? A negative of 1 over v. Okay, remember this is like it's v to the power of minus 2, this thing here. Okay, remember it's v to the power over it, you add 1, you divide by minus 2, divide by minus 2 plus 1, and this is just minus 1, and then you have v to the power minus 1 that will make this v to go to the bottom with a positive power of 1, and then this 1 here is just 1 divided by minus 1. Okay, that is just 1 divided by minus 1, we get minus, and this is the minus. Okay, the minus 1 that we get here took the v from the top to the bottom. Okay, that's what. And then we want to evaluate this integral, this one here, from v1 to v2 as well. Okay, and then we can take this negative outside and then deal with positive of 1 over v only inside. Okay, now let's write the final answers. I can erase here, I believe. We have an equal sign of nRT minus nRT is still there. Ln of, when we put v2 here and then we subtract when we put v1, the resulting answer is going to be ln of what? Ln of the fraction v2 minus nb over v1 minus nb, and then we close the bracket. We know that ln of, for example, the ones that are simple without this nb's, ln of v, evaluate from v1 to from v1 to v2, you have what? This is equivalent to ln of v2 minus over v1, like this, because we have ln of v2 minus ln of v1. So subtractions of the ln is the ln of the quotient of whatever that you are subtracting. Natural log laws allows us to do that. Okay, so that's what happened with this one as well. Okay, so we can write now this as what? Minus that we said we'll take out. Let's take it out. Minus, we put it here, minus n squared a into what? Into 1 over v2. We substitute v2, we get 1 over v2 minus 1 over v1. Okay, and then we close the bracket there. This is now the final answer if we substitute. When you substitute, we open a big bracket just because of the unit joules. Instead of us putting the units inside here, and then we're going to write a long irritating thing. Okay, we don't want to do that. We just want to write one big bracket for everything. So we just say this is the same as work. Work is the bracket of minus. N is 1. We put 1. R is 8.314. T is 300. And then we close the bracket and we write ln of V2. Here, we need to convert them because now we are subtracting NB from, they are in front of the ln, yes, but we need to convert them to SI units because we are subtracting NB from them. And remember, NB and B, they are in the SI units, pascals meters cubed per mole. They are in the SI units. So we need to convert these V's to the SI units as well. So V2 is 5, but we are going to say multiply 10 to the power minus 3. Okay, and then same applies to the bottom one. That is just 5 again. Not 5, is 20. V2. It's V1, 20. Multiply by 10 to the power minus 3. And then we subtract here. We subtract NB. N is 1. B is this one. 4.267. 4.267 times 10 to the power minus 5. Okay, writing it like this, 0.00000, there are so many that they are going to confuse us. You end up there's no space in the calculator, but there's space for this in the calculator. Okay, I'll show you now how to press a calculator now. Okay, now knowing that, here we can write the very same thing, 4.267 times 10 to the power minus 5, and then we can close this bracket, subtract n is 1, a is 0.3, 0.3, 6, 4. I'm gonna write everything down here. Okay, I hope that's fine. This bracket, we are only remaining with this bracket because I don't have space here. The space is finished. Okay, so I should have take this thing this side, far this side, then it will be fine. But then still fine. Can continue here. We have the bracket of what? The bracket of, we are multiplying this one now here. We're multiplying this 0.364 by a bracket of 1 over V2 is 5, multiply 10 to the power minus 3, subtract 1 over V1 is 20 times 10 to the power minus 3. And then we close the bracket there. And then we close the big bracket that I don't have space as well for it. Okay. There are two brackets. There are supposed to be two brackets here. Closing. Okay. Please pay attention to that. I cannot. Okay. I'll just do this so that I can close. Here we close another bracket. That big one. Let me make it square so that it looks the same as that one. Okay, this one is a curved bracket for this first bracket for these two terms there, and then we have something like this. We put it in your calculator. We get W. Okay, we need to write joule here. That the use of the big brackets. The reason why we use big brackets because we wanted to write joule here, and then we say W is the same as what? When you punch the whole thing in your calculator, you should get what? You should get 3,419. Okay, 419 joules as your final answer. Okay, calculating the last one, we can just do it here quickly. We know the answer is that, and then we can put here. We can put here delta U is the same as Q plus W. Okay, and then we can make Q subject of the formula because we are looking for it. Q is the same as this guy here, delta U. That is minus of what? That the one that we calculated before. It was minus 54.6. Okay, we subtract W. It's positive W. We want to subtract it that side. Subtract what? Subtract W is 3, 4, 1, 9, and then this whole thing is in joules. Okay, and then what do we get? We get um the final answer as minus of 34 or 3,474 joules. We put it like this and then we are done. And we can do the last question here it still says CO2 is a van der Waals gas but now compressed irreversible instead of reversible and carried out a constant external pressure. Now you see the word constant is another key word. Constant external pressure. That's what makes it irreversible. Now, like the sketch that I showed you in the beginning of this video, the pressure that is outside is much stronger than the pressure that is inside. Now they are no longer equal. This one has much power to compress, to squeeze this container. It's raping the one that is inside. This pressure that is outside is raping the pressure that is inside now, so that the container becomes so small and quickly. It happens so quickly. Okay, like that. I get like a snip of the finger. You're not tree. It happens so quickly. Now, what do we have? We have that fact that it still remains, whether it's irreversible or not, the fact that W is the same as the integral of dW, where you find your dW as your minus P external dV. Okay, this fact that dW is equal to minus P external dV, it still holds. Okay, now we can continue and say this is the same as but because we know we are integrating with respect to volume there, we can start by indicating here from volume 1 to volume 2. Now that we know we are going to work with volume, and then now that our P external interesting cases, irreversible. Now that our P external is constant, he can go outside of the integral together with the minus 1, so that we have minus P external. And then we have this P external. We don't need to replace him with anything else because we have him here, 1 ATM. All we have to do is to convert to SI units. And then we have the integral from volume 1 to volume 2 of dV, 1 dV. Okay? And this is the same as minus P external. What do we have here? Here we have a V2. We have one integrating constant number dV, you get V, and then you want to integrate it from V1 to V2. Okay, that's your V. You want to work with your V like that, and then this is the same as minus P external into V2 minus V1, and then we close the bracket like that. Okay, and then we can just plug everything in. Before we plug everything in, we need to convert this P external. Our P external is 1 ATM. It's not in the correct SI units, okay? So we'll write there, we know that 1 ATM, okay? This is what we know. We write what we know down. It's the same as 10, 13, 13. I'm doing it for the future, okay? For this one, we can just replace 1 ATM with 1325 pascals. I'm only doing this for the future, by the way. I want to make that one clear. For this one, we can just replace our P external with 1 ATM, which is the same as 10, 25, 13. But what I'm doing here, I'm doing it in case now you have a 3 point something ATM, 3.2, 3.33 ATMs. If you have something like this is how you convert. Okay, I'm doing it for the future so that you know how to do it nicely and quickly. Okay, we don't have time in the exam room for this one, but we can just replace 1 ATM with 10, 25, 13. It will be like that. Now I'm going to write 1 ATM here. 1 ATM. And then I'm going to multiply it by 1. Like I said, putting this one over this one, or this one over this one as a fraction. I'm just writing 1 because we're saying this is equal to that, right? Now, if those two are equal, if I put them on top of each other as a fraction, okay, and I multiply something, this our 1 ATM, with them, okay, what do we have? We have, I didn't change the question, I didn't create my own question, so we have that 1 ATM is still there, okay, but now we are multiplying it by 1. But our 1 is what? I want to put them in such a way that ATMs cancel, okay, so I'm gonna write 10, 13, 25 pascals, okay, over 1 ATM. And then this gives us what? We multiply this by what? We multiply this by our volumes. Our volume V2 is 5 times 10 to the power minus 3. Okay, we are forgetting a negative here. It's this computer that is giving me wahala. And then I'm focusing on something else instead of focusing on what I'm doing now. Because it's very slow. I don't know what's the problem with it. It's so hot. Just finish up these last questions and then we are done. So we have here 5 times 10 to the power minus 3. And then we subtract 20 times 10 to the power minus 3. Okay. And then we close there. And this is now in meters cubed. Okay. It's now in meters cubed. And then the final answer would be what? The final answer would be this one is going to cancel that one. We didn't change anything. You see what we said about 1 ATM. I can replace 1 ATM with 10, 13, 25. It's there. But in the future, I'm doing this conversion here in the one step, substituting everything in, so that in the future you are able to do it if it's not 1 ATM. Okay, you just follow the same procedure if it's 1,537 ATMs. Just follow the same procedure and then you calculate everything. Then from here, we just punch everything into the calculator. Let me show you with this one, because now, why do I want to show you how to press a calculator? Because I see some guys, they just press a calculator. I will show you now. So if I want to write 1 multiplied by 10 to the power of minus 5, I will just write 1. I press 1, and then I use this button, multiply by 10. It's already in that mode. I don't need to come here and press. I don't press that one. I just, if I want to say minus 5, I just press this negative sign here, negative 5, like this. It saves much space on the calculator, much space on the, so that you can type everything in. That long thing that we had to calculate, you will just calculate it easily. Put everything in. Instead of calculating the first one, write the answer down, and then you are eliminating some units because you're not going to write that whole thing decimals down. You're not going to write all those decimals down. Instead of doing that, we just press like this, okay? You don't do this. I see some guys are doing 1. You don't do this. I see some guys are doing 1 times. They press this multiplication button, and then they press 10, and then they say to the power of 3 of or minus 5. It's not good like this. It's wasting space on the calculator screen. Okay, so instead of doing that, if I want to write 1 times, I just 1 multiply by 10 using this button, minus using this one, not this one, not this one. You're going to get it wrong. Minus of 5, like that. This is how you type it in. So please be careful next time. Okay, that's how we avoid that mistake. And then we just punch the calculator here. We get our work as our work 15, 1,520 joules. Okay, and then I forgot to calculate it, but it's the same procedure as for B. We're going to repeat the same thing as for B, and then we're going to make this video longer than necessary. So we can just skip that one. But delta U, to calculate it, you're going to start here. Do the same procedure as we did with B. You remember how you can still remember how to calculate delta U on this question. Section part B of this question that we are dealing with. Okay, you can calculate delta B. It's the same thing, and it's going to produce the same answer, minus 54, I think. I think it was minus 54.6, something like that. You just do the same thing because it's still van der Waals gas. Yes, okay. We are looking at the gas, yeah, van der Waals, and then we are going to use the same van der Waals gas laws to calculate with that pressure that is in the inside now. We're going to ignore the one that is outside. We're going to focus on the pressure that is inside when we are substituting the P's here, and then we get the same answer. Okay. But now the Q, we say delta U, how would we then is the same as what? Is the same as Q plus W. So that our Q is going to be our delta U, that is minus 54.6 joules. And then we subtract W, that is that one that we calculated here. Okay, and then we just substitute there. We substitute 1520 joules. Okay, and then we put like this, and then our Q turns out to be what? Now the system is losing heat. If you touch this system, you're gonna feel that heat coming out because the system is losing heat. It's being compressed and it's losing heat. It's releasing heat out. If you touch that system, that's why we have negative of heat. That's why it's releasing heat. Okay, because it's being compressed. Work is being done on it, and then it's releasing that heat. And then that heat will be of, you will get this much joules. A minus of 1,574.6, but that you can just round it off to be 75 joules. Okay, and we can erase here and view the answers. The answers are all there. If you enjoyed watching this video, please don't forget to subscribe and share this video with many friends. And then we can just end this video here. Thank you very much. Don't forget to calculate delta U of C is the same as calculating delta U of B. We apply the same procedure. We start here and then we push it to until we have du, and then we integrate both sides. We get delta U by like that way. Okay, that's how we get our delta U. Take care. Thanks for watching this video. Good luck with your exams. Please let me know what you would like to watch next. I might do it. I might
Why?
not do it. The pressure is too high.